quantitatively different age distributions that, that George talked about earlier and that I've talked about a little bit. As you've probably gathered, it can be a little bit subjective to say, well, how similar is this bluish line here to this reddish line here? And I want to know what that means geologically, how, I want to make some interpretations about the Earth. And I want to do this in the most objective way possible. And a nice way to do that is to compare age distributions quantitatively. Okay, so this is going to be a really simple example, but I think simple is better when going through this stuff. And learning by example is also a good way to go. So let's go. We have 3 ages. So with low analytical budget, we can only analyze 3 in the sample. So probably not a great representation of the underlying population, but good for this exercise. We're going to stick with PDPs for this. Just a quick note on KDEs. You can do all of the methods that I'm about to talk about with KDEs, but instead of using the analytical uncertainty to specify the width of each of these Gaussian curves, you would make each of those widths exactly the same. So you would say, that would be an assumption, and it's an arbitrary assumption. That's one of the downsides of KDEs is they don't incorporate uncertainty. Okay, so let's say we look at cumulative distributions. Again, kind of a similar thing. I think I have one here. Basically, it's a step function. For everywhere you have an age, you take a step. And that would be, and you add those up as you move from left to right to older ages. And that is going to give you a probability between 0 and 1 on the axis on the right. The axis on the left is for the PDP, and it too is probability. But you don't want to think about the height of the peak, right? You want to think about the area under that curve, because the area under this sum of the Gaussians is 1, it's normalized. So this is going to be some weird tiny number that doesn't make a whole lot of sense. A lot of people actually ignore it, and that's totally fine with the quantitative methods that we're going to talk about. But just note the difference between PDPs and CDFs, because the metrics are going to be a little bit different for quantitatively comparing these. So let's go and look at 2 different distributions. These are very different looking, but how different are they quantitatively? So these aren't continuous functions. They look like continuous functions, but they're actually discretized functions. And by discretized, I mean this is schematic, but imagine there's a dot or a point every 1 million years. So the blue distribution here has some number of points, so there'd be 2,500 points of blue and 2,500 points of red. Okay, and these share the same exact place on the x-axis, and that's going to allow us to do some fun statistics on these distributions. So let's call the red one F and the blue one G. And something that George did, really clever, George, in 2000, you've in the seminal paper, you developed this metric that you called similarity. And so what George did here is he said, well, I want to quantitatively compare these. I want to be really objective here. I'm going to take every point along F and every point along G and multiply their y-axis values against one another and take the square root of that value. So for F and G right here, you take those y values and multiply F by G, take the square root, and that's actually, it's a geometric mean, and sum all of those together, and that will give you a value between 0 and 1. And if you get a 1, that means it's a perfect fit. These are identical. If you get a 0, it's the worst possible match. It's completely dissimilar. Here you can see there's some overlap, which is sometimes this is called overlap and similarity because they share a lot of properties. But here is a 0.3. Well, is that very similar or not? Well, it depends on what you're comparing to, because this is not a hypothesis test. This is a relative measure of similarity. Some others came along a few years later and developed, first it was mismatch, and then by Amidon in 2005, and then Setkowski came along a number of years later and said, I want to calculate likeness. So what he decided to do was take every point and subtract F from G, and then take that absolute value and divide it by 2 after you add them all together. If you subtract that value from 1, that'll give you another measure of how similar these are. And so we have L for likeness. And note that that's going to be different from S. So if you're doing similarity and likeness, they are analogous, but you can't compare them directly to one another. These are all relative measures of similarity. Cross-correlation is kind of a messy code or a messy bit of math, but it's actually quite simple what's happening here. So let's skip the math for now and I'll show you what it's actually doing. We're taking all of the y-axis values and we're cross-plotting them for blue and cross-plotting them against all the y-axis values for red. And you get these weird looking plots. And so you notice that these axes for the red PDP and the blue PDP, they go to the same number here. And that's because, again, you're just cross-plotting every pair of y-axis values. And if you calculate this, r squared, it's just the cross-correlation coefficient of that. And you can see it's very low. So again, 0 would be a bad fit, a 1 would be a perfect fit. And these are clearly dissimilar visually, but now we have this boiled down to a number. Two more metrics, and these next two deal with cumulative plots. So here are the same data that we looked at before, just in cumulative, empirical cumulative distribution, so stair-steppy looking functions. George mentioned the KS test, and the KS test is, it's dependent on this value called D. And D is the maximum difference between if you took CDF1 and subtracted it from CDF2 and vice versa. What's that largest distance there? So you take one, subtract it from the other, and vice versa. You take that absolute value, that's your D value. And you can extend this into a p-value, which is a statistical hypothesis test, but for a number of reasons that I don't have time to go into in this course, p-values are a poor measure of similarity. Basically, they produce too many false positives in terms of hypothesis testing. You might have heard of p-hacking is a big issue in the scientific literature outside of detrital geochronology, and that is another direct result of p-values being having issues, put it that way. I don't want to go too far into detail, but what we do in detrital geochronology is we use this D value as a measure of how similar in a relative sense these are. And here, a high value of 1 is the worst fit. So a 0 is a perfect fit and a 1 is a terrible fit. And you can imagine if these are identical and you subtract them from one another, you would get a 0. So that's why a 0 is a good fit. Last one is a Kuiper test, and the Kuiper test is an extension of the KS test. And here what you're doing is instead of taking the maximum of the absolute value of CDF1 and 2, is you're taking CDF1 and 2 and taking whatever that value is, and taking CDF2 minus 1 and taking whatever that value is and adding them together. In this example, it's going to be the same because this is the biggest gap between them in either case. Oftentimes, the Kuiper test will give a slightly larger value, V value. So V is the Kuiper test version of D. And so my PhD advisor and I, back when I was a student, we did as rigorous as we could assessment of all of these different metrics in this paper that's included in the literature folder online. And for p-values, I'd like to point you toward Peter Vermeesch. Again, he's a major player in this field and a great statistician. The bottom of this paper, if you're curious about why p-values are not such a good idea, I'd like to point you toward his Appendix B in his 2013 paper that we've also included. It's the most concise version of this that I've found to date. So Peter does a good job of explaining why p-values are a bad idea. We also do it in our 2016 paper, which is included as well. We did some more kind of empirical testing and found very similar results that p-values are not a good idea. Okay, so now let's dive into the hands-on part of this. I'm going to show two programs pretty quickly because we have a lot of material to go over. We still have to look at hafnium and trace elements and all kinds of fun stuff. So I'm going to keep this pretty short, but I just want to show you where the buttons are to do the things. That's my ultimate goal here. And so we're going to first start with DZstats, and I'm on a Mac here, so I'm going to go open up DZstats. And then I'll talk a little bit about multidimensional scaling, which is really an extension of these different comparison measures that we've incorporated into DZstats. And I'll talk a little bit about each of these as I go. Just a quick reminder, the hands-on guide is really kind of a step-by-step little cookbook to reproduce everything. I think Sarah's been through this a few times now, and she had a good time going through it, I'm sure. But it's basically, it'll give you a little bit more information and a step-by-step walkthrough of each of these programs. I'm going to keep it pretty loose here, but basically we're doing this activity 2 and activity, see, it's a little long, so we're not going to go through every bit, and activity 3. So that's included in the Google Drive. Okay, so DZstats, basically all of these different comparison metrics, they already existed, but they didn't exist in a single place and in an easy to use fashion. And so my PhD advisor, Joel Saylor, and we said, well, what if there was a program that could just, with a click of a button, give you the answer to the quantitative comparison of like 10 data sets? And the answer to that question was no, it didn't exist. So we're like, okay, well, we should figure out how to build it. And so the code is not the most pretty code in the world if you're wanting to dive into it, but it does functionally work, I think, quite well. I'm going to start with a very simple example. 2 sample compare. We're going to click on that. We're going to stick with probability density plots here. So not a ton of time to go into the arguments for or against PDPs and KDEs, but again, that's in a short course from yesterday that you'll have a link to. Okay, so this is the most simple version of this program. Basically, we're going to take 2 data sets and only compare those 2 on top of one another. So we're going to need to load 2 data sets. So go ahead and head to your browser and go find some data. So in the short course materials, again, all caps input. Now we're going to go into DZstats. And what I want to do is compare that 120 and the 1200 output. Give you a quick look at what these data look like. It's just 2 columns of age and uncertainty and all of the data reduction. And these are saved as a CSV file. So no names, no headers or anything like that. And so go ahead and load the 120 for this one here. And you should see the path populate and just click plot. And that'll only plot that one. And this is the distribution from that first reduction we did as a PDP and a CDF. Now, what we want to do, let's compare that to the second one that we reduced. So go to browser again, head off to your desktop or wherever it lives on your computer, input quantitative comparison, and here's that 1200 an hour. So this is the one that we reduced earlier. So open that. And it won't plot it automatically. You have to click plot once you see the path populate. And so notice they look a little bit different, right? So this one has 1,000 or so ages. This one has about 100. So let's overlay those. And I think this is really going to get across a major point that George was talking about earlier in terms of large N detrital geochronology. So we can zoom in on these here. Let's zoom in on just this younger part of the age spectrum. The blue is the larger data set. So this has 1,000 ages in it. And the red, this really spiky looking one, that is the smaller data set, as you can see over here. And again, these came from the same rock, the same separate, the same mount that never left the machine. It's just we analyzed more ages, and you can see how different they look, both in PDP and KDE. And now we can do is calculate statistics by clicking on this button here. And this was the dream button that Joel and I wanted when we were talking about this back when I was a student. But I want that button, just show me all the answers. And so you notice cross-correlation, likeness, similarity. These give slightly different answers. So a 1 would be a perfect fit here. You get your D statistic from KS. Because we're trying to be transparent, we put the p-value in, although we caution everybody in using that value for any interpretive work. The V statistic, again, a 0 is a perfect fit there. Would encourage using the V and not the p-value. KS, 0 is a perfect fit. Cross-correlation, likeness, similarity, 1 is a perfect fit. But now we have a numerical assessment of how similar these are, right? And so you can start to, if you have more data from some giant field area or a compilation, you can very quickly start to assess the similarity or differences among multiple samples. And that's where we're going to go next. But maybe it's a good time for me to pause it here and see if there's any questions. I'm going to press on them. So I'm going to close out this module. We're going to go to intersample comparison. And so we're going to stick with PDPs. And intersample compare, now we're going to load a data set that has multiple samples, not just one at a time. Okay. And so again, like most of the programs that myself or Joel and I have built over the years, I usually stick it up here in the top left, a browser window button, and go to your desktop, try to find it. Desktop is going to be full by the end of this course. Okay, so CP40 sessions 1 through 8. And so I'm going to take a quick look at this. So now we have the 8 tests that we did for that recent paper. So we said, okay, let's test. This first sample is at 120 an hour, 120 analyses per hour. So there's not very many ages. The next one, the next 4 columns are age uncertainty of 300 an hour. And so you have more ages. And then 600 an hour, the next one, and then these last 2 samples kind of go on and on and on and on and on. So lots of data for the last 4. The organization of this will come into play in just a minute. So I thought I'd take a second now to show you the input. Again, no names in there, no headers. Just open that up. And you should see this populate and click on plot. And that's how you bring the data in. And so 1, 2, 3, and 4, all the way up to 8 samples. The darker ones are on the right side of the spreadsheet. And so those are the larger samples sizes, and the cooler colors are the smaller sample sizes. And you notice a couple of things, right? The more spiky, more dispersed data are the more spiky ones with the ones with fewer dates for those age distributions. We also have a cumulative plot here, and those look pretty similar to me. But again, here's that magic button that Joel and I always dreamed about. And so what this is a pairwise matrix, or a pairwise comparison matrix, where we're taking sample 1, 2, 3, 4, all the way to sample 8. So the 120 analyses per hour, 300, 600, 1200, and comparing them against all of the other samples. So a 1 is a perfect fit. So if you compare sample 2 to sample 2, and that doesn't come out to 1, something's terribly wrong with your program, right? And so this was encouraging when we were first building this, but now we have an assessment. Okay, well, what if I want sample 3 compared to sample 4? Okay, that's a 0.6 for cross correlation. And that was a moderate size sample. What about sample 8 versus 7? Those were the bigger samples. And notice those numbers they tend to get larger, right? And that makes sense. You have more information about those distributions, and they're more similar, as I showed you before, in this plot here. Oops, not that plot. This plot here. So as a reminder, so session 1, 2, 3, 4, 5, 6, 7, 8. And you can see visually that, yes, they're getting more similar, but now we have a numerical assessment of how much more similar they're getting. Let's close that out. So you can check this out for similarity. So when I still use, a lot of people still use, this is George's metric that he came up with, likeness. So you get a matrix, and you can copy these into an Excel spreadsheet. But what we did is we figured, well, what you really want to do is look for consistency among the different metrics to see if, if you're getting wildly different results for cross-correlation and similarity, say, hey, wait, time out, what's going on? This is, there must be something going on in my comparison setup. So what we did is we put this button here, run all tests and export to spreadsheet. So I'm going to say DZstats output and put that on my desktop and save it. A quick note to users of Windows 10, there is a bug with this button I found last night. And it seems to be only on specific Windows 10. So Windows 7 and before it worked great. Some Windows 10, I think it's a permission issue thing. I fixed it last night, and the new version's on GitHub and it's on the Google Drive. But if you had downloaded everything a week ago, this button won't work for some Windows 10 users. And again, I think it's a permission error, but just a heads up, if it's not working, then that's why. Compatibility is our is a never-ending struggle. Okay, so you should, if you were able to export this, you'll get a sheet that looks like this. I'm going to zoom in here a little bit. So here are all of the different metrics. I tend to just delete the p-values because, as you'll read in Vermeesh's paper, they are not useful for what we do in terms of comparison. So I actually just get rid of those right off the bat. And then I like to add some labels. A newer version will incorporate these labels. But this was 120, 120, 300, 300. These are the rates of acquisition that we ran for these different, and call those our sample names, for example. So transpose that. And so those would be our sample names. And what I like to do, I like to format it so I'm not looking at a huge string of numbers, but maybe, I don't know, 2 decimal places. You might stick them in the middle. But the most important thing that I like to do is, and to avoid any political things, I'm going to go green and red here, where green is very good fits and red is perhaps not so good fits. And so this is called conditional formatting in Excel. And you can do this for all of them. I'm actually quite used to looking at blue and red, so I'm going to go the political colors. Why not? Hey, it's voting season, right? And so what I like to do, and in future versions it'll automatically do this for you, is look for consistency among the metrics here. So I'm going to format this, make them all just 2 decimal places, put them all in the middle, and just organize things accordingly. And so you get a visual assessment of this. Okay, like you can see that the larger data sets are becoming more and more similar to each other. And no matter what, every data set compared to the smaller data sets is very dissimilar, even to itself, right? So very low values versus higher values as you go to larger and larger n, or larger and larger sample sizes. And so again, if these are inconsistent, you might want to say, hey, time out. I need to interrogate my data input a little bit more. Remember these values, a 1 is a perfect fit and a 0 is a bad fit. And the cumulative distribution function metrics, these are, a 0 is a perfect fit. So what you need to do in your conditional formatting is use the inverse. So if I went blue to red, now I'm going to go red to blue. And you should see the same, you should see a similar sort of thing here. Red to blue. And if you're not seeing a consistent result, then yeah, again, timeout, what's going on here? Yeah, so I'm gonna pause there because the next step that I want to take is to take this numerical assessment and turn it into something that's even easier to interpret through multidimensional scaling. So are there any questions out there in Zoom land?
So far in the chat, you're good.
Yeah, I think the recording it perhaps might be saving us because people know they can go back if they need to. So Yeah, and again,
I have a question. I'm sorry, I missed the starting of it. Can you, when you started your intersample comparison, what was the file path that you used?
I went to browser.
Okay.
And I put the download from the Google Drive on my desktop, so the short course materials there, all caps input, DZstats. And it's this one that has multiple samples. So
Oh, okay, cool.
yeah, so take a quick look. There's multiple samples here.
Perfect. Okay, thank you.
And that's it for DZstats. Are there any other questions before I move on? I think I gave myself, yeah, I've got 14 more minutes on this. I'm trying to keep myself on track here. Because as nice as a block of numbers is to stare at, there is an easier way to interpret these data and detrital distributions in general, and one that's picking up steam every year. It seems like there's more and more papers that are using the technique that I'm going to show. So I'm going to delete this. Don't need that anymore. And we're going to use the same quantitative metrics, but we're going to visualize the results in a different way. And for that, we're going to move on to DZmds. And again, as a reminder for folks that might not have gotten back from lunch in time, all of this is written out in some version in the hands-on guide. So this would be activity 3. But I'm not going to follow this cookbook. But if you get lost or later on you want to try this again, go ahead and try that cookbook first. And if you get stuck, by all means, reach out to me. I do not mind. This is what I like to do. Okay, so the input for DZmds, again, is going to be age distributions, but it's going to be a little bit different because here we actually need the sample names. So for example, here's an example data set that we won't look at, but if you have sample names, so this is some data that I generated years ago, this would be age and uncertainty, but you need the names. So like if you have, say, the Kuiper formation, you might want to call that one the Kuiper, or something like that. So, and I would encourage you, if you're using DZstats in a similar way, put your younger samples on the left and your older samples on the right, because that will work well with the program that we just looked at. So I usually go from young to old in these. But yeah, so you'll need headers. So you'll need sample names for the multidimensional scaling. Okay, so similar to the programs that we've made over the years, we have this some version of select file on the left. We'll go to desktop and find our data. All caps input. Now go into multidimensional scaling and select, let's look at the same data that we've been looking at. Again, there's a comparison of slower versus faster rates of acquisition and smaller and larger data sets, all from the same exact sample. Let's open that. There are a couple of options. See, Joel took the lead on this interface, and he liked to number them. So you have the option of 1 or 2 input sigma for your data. That's only going to really matter for your PDPs. These are 1 sigma data. If you want to use a KDE, you can add a kernel bandwidth, so 10, 20 million years, however you like. I'm going to stick with PDPs for this. You have the different kinds of comparison metric. So let's stick with cross-correlation. And there are some different criterion. And this will become apparent in just a sec what this means, although I'm not going to go into detail. I've written up a little paragraph on what these different things mean in the hands-on guide. So we'll defer to that for now. For things you need to do to see the plot, the first thing you need to do is get dimensions. So get MDS dimensions, this button down here, number 6. Go ahead and click on that. And what you'll see is this weird plot that says stress on the y-axis and dimensions on the x. So, okay, well, what on earth does any of that mean? This will become clear once we plot the next one. So let's first plot this in 2 dimensions. So change this to a 2, you can select 3, that's fine. But what I want to do is plot the MDS, which will be the multidimensional scaling plot on the right, and what's called a shepherd plot here on the left. So click on plot, and you'll see a couple of weird looking plots. So let's start with the shepherd plot, because this will help explain the scree plot, this thing scree plot above it. So what MDS attempts to do is to take your dissimilarities. I'm going to go back to my DZstats output. It's attempting to take your dissimilarities, so this block of numbers, and it needs to be dissimilarities. So actually it takes cross correlation and subtracts it from 1. Or if you have something that already is dissimilarity where 0 is a perfect fit, it'll take that dissimilarity block of numbers and it says, okay, I want to force these numbers that have no spatial relevance or information and force them into a Cartesian box or cube. So it's saying take these dissimilarities on the x-axis and convert them into distance on the y. And how good that transformation of the data is called stress. Stress is kind of a subjective number, but to give you an idea of a good guideline, Peter Vermeesch, again, he's been in the conversation quite a bit. Peter was really the pioneer in terms of bringing this into the detrital geochronology community. In 2013, he put this out there. This is the same paper that talks about p-values at the end. And so I encourage everybody to read this. It's a pretty short, it's a bit dense, but give it a few reads. Again, it's really short, but it's all packed in there and gives a nice example. And he talks about stress here. And this comes from Kruskal. This is seminal work on multidimensional scaling from a completely different statistical field, the actual statistical field, because this was an old technique that was only recently brought into the detrital zircon community because of Peter, because of the work he's done. The table that I want to point out here, this is the stress table. So a bad transformation would be like 0.2 and higher. A fair transformation, 0.1, good, excellent, and perfect, heading towards 0. So coming back to here, this value, if it's 0.2 or higher, depending on your data set, you'll see these blue dots start to fall off of this kind of 1-to-1 line, and your stress value will be high. And what that means is this Cartesian representation, again, of your dissimilarities is not a good representation if that stress value is high. That's what that means. Okay, in the scree plot here, you can imagine as you go to higher and higher dimensions, there's more freedom in a higher dimensional space. This stress value should go down, and in fact it does because it's plotted here. So if we do this in 3 dimensions, you can change from 2 to 3. You don't have to get the dimensions again, you've already done that. And you actually know the value of the stress, it's going to be much lower. So this is, there are more degrees of freedom here in which to, again, you're taking your dissimilarity matrix here, and now you're forcing it not onto a map, but into a box, like a big Cartesian box. And what this does is it runs a code, an algorithm that will iteratively arrange this. And basically it will start with the most dissimilar, move my zoom stuff here. It'll start with the most dissimilar here. So 0.15, and those will be the bounds on that, and then on that cube. And then it'll take the next most dissimilar, like these guys here, and then it'll try to pack those in and pack more in and more and more in until they all fit into the smallest arrangement in Cartesian space. And so something that doesn't typically get across when, even for people that have used this technique a lot, that multidimensional scaling plot is at its core a degradation of the data. You lose information from going from this space, the numerical space, the raw comparison, to multidimensional scaling space. When you go to Cartesian space, this representation by nature does degrade the comparison a little bit. But that degradation is 100% worth it because now you have a visual representation of these data. You can grab this little circle tool in the top left, and you can start to spin this around. And what you can see is, as we saw with the results out of DZstats, 120 an hour with about 100 analyses that came out of that are more dissimilar than everything. And same with 300 an hour. And then 600 and 1200 an hour. Remember, these produce much larger data sets, and these were much more similar. And so if I put this right next to this guy here, let's make this window a little smaller. Let's put these side by side. So now you can see that 120 an hour visually is going to be very different from everything else. And that's the same thing you get in multidimensional scaling space. And also that's what you get from the numerical form here. So lots of ways to deal with your data, right? So you can look at it visually. It's a great first step. It's a necessary first step. Then you could quantitatively compare it here in numerical form, and then take it into another visual representation of this numerical comparison. So lots of ways to deal with it. There are a lot of parameters here that I'm not going to have time to go into, but I encourage you to click around and see what kind of different results you get, right? So if I click on likeness and leave the stress, this type of stress, get the MDS dimensions, notice that scree plot changes. You get a slightly higher shepherd plot stress value. Notice that these are kind of falling off, and you get a different picture, right? And so I guess just a couple of cautionary notes as I wrap this up in the next couple of minutes. Just like in the in DZstats, the results of the quantitative comparisons, I think, at least in my experience, consistency among the metrics is your best friend. If things are not consistent, then something is wrong with your comparison setup. If we go back, this will probably become a little more obvious if we go back to 2 dimensions. So let's force this into a map, not a box. And so here's for likeness. You see that, well, okay, yeah, 120, they're basically setting the bounds of that box. 300, they're dissimilar, and then you start getting more and more similar. Go to the Kuiper test. Remember, this is based on that cumulative plot, the cumulative distribution function. So get the dimensions and then plot the plots. And here, again, it's a pretty high stress value, meaning that the transformation from numerical form here, dissimilarity on the x-axis, is not a great transformation to Cartesian space. So rules of thumb, if you're making a figure for a manuscript, you probably want to stick with a 2-dimensional space. You can imagine you're not going to be able to open up a paper, at least not these days, and spin around a figure and have fun with it like that. Because if you just pick one of the projections of this, you can start to get pretty misleading, right? This is going to show you that, like, I could probably force this to show that, wait, yeah, 120, that looks real similar in this projection, right? But we know that it's not. And so if you're in 3 dimensions, be very careful, unless it's really obvious. At least I hoped it was in the paper that we just put out there. I thought it was obvious enough to keep it in 3 dimensions here. This is in that paper in press. But in most cases, I usually stick with 2 dimensions, unless it's this obvious. You try to put some guiding arrows in the box there. So yeah, that would be one kind of rule of thumb. Stick with 2 dimensions, and the second rule of thumb is make sure that your stress value is relatively low with whatever you go with. And the third is look for consistency among the different metrics. And so if these things are coming out wildly different, then time out, reassess your model setup. It's always with any of these comparison measures or anything model based, garbage in, garbage out, right? That always holds true. So I think that's time. I didn't get a chance to talk about these different how stress is calculated. Again, I will defer to Peter Vermeer's paper. This 2013 paper does an excellent job of walking you through each of these steps. And I've done my own little kind of layman's write-up of that in the Handson. So cool, that's what I got for you. I guess probably take a couple of questions, but I will let Sarah and George let me know if there are any in the chat.
Yeah, I think people can audio on, video on if you have any questions about that tool. Remember, this is a set of tools that's available really for data from any lab, any format. All you have to do is have a column of ages and uncertainties, and off you go. They could come from any type of instrument, any kind of data.
Yeah. I put, I showed this earlier, but I've stuck this on my own academic website, but it's all linked to Lasercron's website, so it should be easy to find. We're in the process of building video tutorials for all of this stuff. I gotta say, not to blame the coronavirus for everything, but it has certainly slowed the progress of that down. But so for HCalcML, there's some video instructions, but there will soon be the same for DZstats, DZmds, all of these fun little quantitative assessments of data, these programs that we've made over the years. So that, I think Sarah shared those links earlier, but you can always find it through the Lasercron website as well. But lots of information out there in PDF form, but soon to be videos.
I guess I'll just jump in and offer kind of a high-level perspective that, in the past, detrital zircon geochronology has been primarily a visual kind of qualitative style of analysis where you see two PDP curves and you just say, oh yeah, those are similar, those are not similar, these look better than that, and it's very qualitative. I think what we're seeing from Kurt and Joel and Glenn and Peter, the people who are doing these kinds of analyses, is kind of the whole future of doing detrital zircon geochronology. It's taking out of the qualitative world and it's making it more quantitative. I think there's a lot of potential to make our science a little bit more accurate, a little bit more reproducible. I'm pretty excited about having these new tools. So I hope you take an opportunity to dive in. They're actually very simple to use. I guess I find HCalcML just a little bit more complicated. There's just more options because it's such a rich package of software, whereas these plotting tools and statistical analysis tools, they are super simple.
The only hiccup is formatting your data properly. So not all of these programs take the same format of data. Just make sure it's the right format before getting frustrated with the program.
Yeah. Well, I mean, I tell this to pretty much everybody. Something that if you're really stuck, just send me an email. Like something that'll take you an hour or something and waste your time will take me like 5 seconds to answer an email and say, oh no, it's this, do this, and then you'll be off and running. And it just saves a lot of people time, and I'm happy to do it. If I don't answer, again, just email me again. It means I got buried, but I'm always happy to do that because for me, it's usually a very easy question. For somebody who's looking at this stuff the first time, you don't know where to start, right? I mean, I remember looking at my first user interfaces that Todd Ehlers made for Thermocron. Like, what is this? So I understand how it can be, but data formatting is a big one. And so if you get stuck, yeah, just send me an email.